Hello students, my name is Mihir Mehta. In the last class we were discussing about the derivation on the heat rise in the machines with respect to time and the variables associated with it. Today we will see the numericals based on the same. The numerical data says a field coil has a heat dissipation surface of 0.15 meters square and the length of the mean turn is 1 meter. It dissipates loss of 150 watt. The emissivity being 34 watts per meter square. Estimate the final steady temperature rise of the coil and its time constant if the cross section of the coil is 100 into 50 mm square. Specific heat of copper is 390 joules per kg degree centigrade. The space factor is 0.56. The copper weighs 8900 kg per meter cube. So this is nothing but the density of copper. So now let us move to the answer to this particular numerical. Now first let us calculate the volume of copper. Now the volume of copper, as you can see here, is given as 1 into 100 into 50 into 0.56 into 10 raised to minus 6. Now let us see that how did we get this. Your 1 is nothing but the length of the mean turn. Now that is given in meters, so we'll remain it as it is, multiplied by the cross section area of the conductor, that is 100 into 50. So as we say that it is 100 into 50, but this is in mm square. We need it in meters, so that is why we multiply it with 10 raised to minus 6, multiplied with the space factor, which is 0.56. So when you multiply all these terms, the final that you get is 2.8 into 10 raised to minus 3 meter cube is the volume of copper which is being used. Moving ahead, the weight of copper. Now since we know the volume of copper, we know how much copper weighs per meter cube. So from these two data we can find out the weight of the copper, which is denoted as GC, is nothing but 2.8 into 10 raised to minus 3 multiplied by 8900, which gives me nothing but 24.92 kgs. So this is what we have computed from the given data. Now let us see what do we need to find out. If you look at the question again, it says estimate the final steady temperature rise. Okay, final steady temperature rise is to be estimated, so that is theta m. Okay, that is need to be found out, and its time constant. So time constant is nothing but th. Now these are the two terms that we need to find out. So as we know, the formula for finding theta m is nothing but q upon s lambda. Now if you are not able to recollect what is q, what is s, what is lambda, I would like you to refer to the derivation that we had carried out. Your q is nothing but your heat loss or the loss dissipated, that is 150 watts. Your S is nothing but the surface which is dissipating that heat, that is 0.15 meter square, multiplied by your lambda is nothing but lambda is the emissivity, and that is 34 watt per meter square degree centigrade. So this would be multiplied with 34. So if you calculate this, what you will get is 29.4. Now theta m is nothing but your final steady temperature rise, so this would be nothing but degree centigrade. So therefore you can say the final steady temperature rise is 29.4 degree centigrade. Moving ahead, we need to find the heating time constant. Now, you know the formula for heating time constant. TH is nothing but capital G into H upon S lambda. So instead of capital G, what we have here is GC with small h into capital S into lambda, where capital G, as we have calculated, is 24.92 kgs multiplied by H. What is H? H is nothing but the specific heat, and that is 390, specific heat of the copper, divided by, again, S is the surface, that is 0.15, and lambda is the emissivity, that is 34. So once you calculate this, the answer you get for this is 1906 seconds. Now why seconds? Because this is your time constant. So therefore, the heating time constant for the given data is 1906 seconds. I hope you enjoyed solving the last question. Moving to the next question, let us read the data of the numerical. The existing coil of the electromagnet has a cross section of 120 into 50 millimeters square and a length of the mean turn of 0.8 meters. It dissipates 150 watts continuously. Its cooling surface is 0.125 meters square, and the specific heat dissipation is 30 watt per meter square degree centigrade. Calculate the final steady temperature rise of the coil surface. Also, calculate the hotspot temperature rise of the coil if the thermal resistivity of the insulating material used is 8 ohm meter. The space factor given is 0.56. So let us move to the solution of this problem. Now first, let us find out the final steady temperature rise of the coil surface. So let me write the final steady temperature rise of the coil surface, which is given by the formula theta m is equal to Q upon S lambda, where we know that Q is 150, the dissipating surface S is 0.125 meters square, and the emissivity is 30. Fine. So this, after calculation, what you get is 40 degree centigrade. Now moving ahead, we look at the effective thermal resistivity. So what is effective thermal resistivity? So we can find out the effective thermal resistivity with the help of a formula which is rho 0 is equal to rho I into 1 minus SF raised to 1 by 2. Now where rho 0 is nothing but resistivity of the conductor, or we can say the effective thermal resistivity of the winding. Your rho I is the thermal resistivity of the insulator, and your SF is nothing but your space factor, or it can also be denoted as the copper area by the total winding area. Now moving ahead, if we look at the values provided, we know that the insulation, the resistivity of the insulation material provided is 8 ohm meter, and the the space factor SF, the value for the space factor is 0.56 and whole raised to 1 by 2. Now when we multiply this entire term, what we get is 2 ohm meter is the effective thermal resistivity of the winding. Now we need to know the loss Q. So the loss is Q is given by 150 divided by 120 into 50 into 10 raised to minus 6 multiplied by 0.8. Now when you multiply these, what you get is 31250 watt per meter square. Now from this, we'll move ahead to the temperature difference between the coil surface and the hot spot. So to find out the temperature difference between the coil surface and the hot spot, between the coil surface and the hot spot is given by theta 0 is equal to Q into rho into T square upon 8. Now in our case, the theta 0 would be Q into rho 0 into T is nothing but the thickness divided by the 8. So the value of Q is 31250. The value of Q0 is 2 ohm meter, so multiplied by 2, and T square. Now T is nothing but the thickness, that is 50, since it is in mm, converting it into meters, so 10 raised to minus 3 T square. So squaring this term divided by 8. Now when you solve this particular term, what you get as an answer is 19.5 degree centigrade. So the temperature rise of the hot spot, therefore the temperature rise of the hot spot is nothing but 40 plus 19.5, that is 59.5 degree centigrade. So this would be your final answer. So I hope you're not finding it difficult to solve the numericals. If you have any doubt, you can get back to me on the mail ID provided in the description. Moving to the third question, the heat dissipating surface of a 7.5 kilowatt totally enclosed induction motor can be approximated as a cylinder of 0.6 meters in diameter and 0.9 meters in length. The motor can be considered to be made up of a homogeneous material weighing 375 kg and having a specific heat of 725 joules per kg degree centigrade. The specific heat dissipation from its surface is 12 watt per meter square degree centigrade. Find, or let's say calculate, the temperature rise of the machine at full load if the efficiency is 90%. Second, find the thermal time constant of the machine. And third, the rating of the machine for the same temperature rise if the machine were screen protected with a specific dissipation of 25 watt per meter square degree centigrade, and let us assume that it has the same value of efficiency, that is 90%. Now, since it is given in the question that we have to assume the machine as totally enclosed cylinder, so let us take a enclosed cylinder and let us assume that this induction motor has been mounted vertically instead of horizontally. Now, if you look at the diagram, the total heat dissipating surface would be the outer cylindrical surface plus the two end surfaces. So that is the top part and the bottom part, and the curved surface of the entire body. So this all would be included in the heat dissipating surface of the induction machine. Now, as we know that the curved surface can be calculated as 2 pi r into h for a cylinder. Okay, so in this case I am merging 2 into r, and the h can be taken as the length of the machine. So for me the formula would be pi into d into the length of the machine, that is L. Now, talking about the top surface and the bottom surface, now since this is a regular cylinder, the top and the bottom part would have the same area, so which would be equal to pi r square, but since we do not have r, this can also be written as pi d by 2 square, or in other words pi by 4 d square. Now this is only for one particular part. Now when we are talking about both the top and the bottom, so my entire dissipating surface S would be equal to my pi dl plus twice of pi by 4 d square. Further substituting the value, we get S is equal to pi multiplied by the diameter is 0.6 multiplied by the length is 0.9 plus 2 into pi by 4 multiplied by 0.6 whole square. So on solving this entire equation, you'll get this value as 2.26 meters square. So 2.26 meters square is the dissipating surface. Now there is another term which is given in the numerical data, which is efficiency. So let us talk a bit on efficiency. So whenever I ask a particular student that how would you define efficiency, so normally my student replies that it is nothing but the output of a particular machine divided by its input. Now the same fraction can also be written in another two ways. Let's say I can write my output as input minus losses divided by the input, or it can be also written as the output divided by the output plus losses. Now here in this case, let me consider the last part. The reason for doing this is I am already aware about the output as well as the efficiency. So again, rewriting this particular equation, so this would be efficiency is equal to output upon output plus losses. Now I am aware that my efficiency is 90%, but if I don't write it in percentage, I can write it as 0.9 is equal to my output is 7.5 kilowatt, the heat dissipating surface of a 7.5 kilowatt. Okay, so 7.5 kilowatt can be written as 7500 watts divided by, again the output is 7500 plus losses. On solving this, I get my losses, which is nothing but capital Q, which is equal to 8.33 watts. So now when I want to find out the final steady temperature rise, so the final steady temperature rise is nothing but, as we have seen in the previous numericals, Qm is equal to, theta m is equal to Q upon S lambda, where Q is, as we have calculated above, 833 watts divided by S, which is my dissipating surface, that is 2.22 multiplied by the lambda, whose value is 12. So again, further solving this, you will get the answer as 30.85 degree centigrade. Now that is the final rise in the temperature. We also need to find out the time constant, the heating time constant. So let us first write down the formula for the time constant, which is nothing but TH is equal to capital G into H upon capital S into lambda. Substituting the values ahead, the value of capital G is 375, the value of small h is 725 divided by the surface value is 2.26 and the value for lambda, that is the specific heat dissipation, is 12. On solving this particular term, what you have is given by 10025. Now the answer received is in seconds. For converting it into hours, I'm sure you will be able to do it. So convert this number of seconds, that is 10025 seconds, into hours, and you'll get it as 2.79 hours. Now, we have been told that the machine has been screen protected. It is a screen protected machine. So we have already solved the first part, we've solved the second part. Now coming to the third part, that for a screen protected machine, our theta m would be 30.85 degrees centigrade. Our S is nothing but 2.26 meters square, and our lambda is 25 watt per meter square into degree centigrade. In this case, the allowable losses, now just making Q as the subject of the equation, so Q is nothing but theta m into capital S into lambda. Okay, now further resubstituting the values, that is 30.85 multiplied with 2.26 multiplied with 25, and the losses that you will get is 1743 watts. Now, these are the total allowable losses. Now again, we have been told that the efficiency is same. So again, coming to the equation of efficiency, where efficiency is nothing but my output upon output plus losses. So in this case, as we know that the efficiency is same 90%, so I can write it as 0.9 is equal to my output, which I need to find out, upon output plus the losses which I have calculated, that is 1743. On solving this equation, I'll have my output as, on solving this equation, I'll have my output as 15687 watts, or it can be written as approximately 15.7 kilowatts. So I hope you have understood the numerical, and I have tried to attempt this, okay, in a very simple way. I've just placed the formulas and substituted the values. These are the numericals which are reviewed from the book named A Course in Electrical Machine Designs by the author A.K. Sawhney, So you will get more informations on the particular numericals as well as the methods of solving them in this particular book. Thank you. I hope you enjoyed the session, and for any particular doubts you are allowed to mail me and you will get a reply accordingly. Thank you.